The average car slows down from 30 miles per hour to 15 miles per hour, which for a car of about a tonne is a loss of kinetic energy of 338 kilojoules. We are proposing that we harness a portion of that energy and use it to power streetlights. Our bumps would be the next stage of evolution for speed bumps, in which their main purpose would not be to slow down traffic, it would be to use the waste to produce green, renewable energy to power streetlights. Hence itself would increase the safety of the road, making it easier to drive in the dark, and the streetlights would make it safer for pedestrians.
Now the resultant force of the bus, the pad and the counterforce as the bus goes over the pad would be the 13,150 G, the 3,000 G for the plate itself, and then the counterforce of 3,000 G. Now the 3,000 Gs will cancel out, giving us just 13,150 G there. The work done is the force times by the distance travelled, which is 13,150 G newtons times 0.1 meters, giving us 12,887 joules. Given that power is worked done over time, we use T to be 60 seconds, assuming that 1 bus per minute passes over the plate on average. So the power would be 12,887 joules over 60, giving us an average 214.8 watts to 4 significant figures.
I will now discuss how our model can be improved upon in the real world. It involves using multiple pads rather than a single pad, but to do this we've had to make two assumptions. The first one is that the vehicle acts as a particle, such that the pressure pad experiences the vehicle's total weight and therefore also experiences the total support force. The second assumption is that only one pad experiences the vehicle's weight and support force at the same time, and therefore only one pressure pad experiences the pressure at a given time. And then as we move over to do these two diagrams, we can see this one is of a single pad called alpha, and then this second diagram is of a pad of n multiple strips. You can see by the diagrams, every single pad has the same length, so we just call it L. But for the width, pad alpha is width alpha, but because the second scenario has been split into n strips, all of equal length, and they all sum to the same width as alpha. Recall that area is length times width. Therefore, we know that the area of this pad is the area of the sum of all these individual pads. Therefore, a simple rearrangement showed that the area of all these individual strips is 1/n the area of the alpha pad. In our assumptions, we defined that the force is mg minus s. And now recall that pressure is defined as force divided by area, such that in our model, pressure equals mg minus s over A. Now, applying it to the left-hand diagram first, we get this equation. And then when applying it to the right-hand diagram, we get these following equations, and they all produce the same output, because all the strips have the same area. But notice here, for the alpha pad, it has area alpha, but for the smaller pads, it's 1/n the area of alpha. And for our right-hand diagram, n must be an integer greater than or equal to 2 in order to have multiple strips. And therefore, the left-hand side of this equation is always strictly greater than the right-hand side of this equation. And therefore, this is the proof that shows that the pressure of each of these individual strips in the right-hand diagram are always equal to each other, but are also always strictly greater than the pressure of a single pad.